Welcome. Today we explore the architecture of the atom and the philosophy of complementarity, a comprehensive look at the life, science, and legacy of Niels Henrik David Bohr. Bohr did more than just map the subatomic world, he reshaped our fundamental understanding of reality itself. We will trace his journey from the development of his iconic atomic model to the introduction of complementarity. The profound philosophical insight that seemingly contradictory properties are both essential to describe quantum phenomena. Join us as we examine the revolutionary contributions of a man who bridged the gap between classical physics and the dawn of the quantum age, leaving an indelible mark on the history of science. Today we examine a mind that redefined reality. Our journey begins with the physicist who decoded atomic structure and fathered quantum mechanics through his landmark 1913 trilogy. We then encounter the philosopher, the architect of complementarity who navigated the deep epistemological debates against Einstein to define modern reality. Finally, we see the statesman, a figure who transitioned from a Manhattan Project consultant into a global advocate for the UN open world and a founder of CERN. Together, these three pillars reveal a brilliant legacy that fundamentally transformed our understanding of the physical world and the pursuit of international cooperation. We now encounter the impossibility of the classical atom. While the Rutherford model successfully identified a dense, positive nucleus orbited by electrons, it simultaneously unveiled a profound scientific crisis. According to the established laws of classical electrodynamics, an orbiting electron should constantly radiate energy, causing it to lose momentum and collapse into the nucleus in a catastrophic classical death spiral. This theoretical failure implied that stable matter simply could not exist under Newtonian physics. It was a moment of reckoning that proved the old rules were no longer sufficient. A radical new architecture was required to explain the very stability of the physical world. To resolve the classical crisis, Bohr proposed a quantized architecture. He introduced stationary states, where electrons inhabit fixed, discrete orbits without losing energy to the death spiral. Stability is maintained until a quantum jump occurs, an instantaneous leap between orbits where radiation is emitted or absorbed, governed by the relation E equals hc over lambda. This model provided the ultimate proof by accurately predicting the observed spectral lines of hydrogen. By successfully bridging classical mechanics and the burgeoning quantum realm, Bohr's 1913 trilogy replaced chaotic collapse with a precise, orderly blueprint of the atom, laying the foundation for modern physics. In 1921, Niels Bohr's institute became the Copenhagen Mecca, the epicenter of a scientific revolution. Guided by Bohr's insight that quantum evidence often defies a single description, a legendary circle of collaborators gathered to redefine reality. Werner Heisenberg pioneered matrix mechanics and the uncertainty principle under Bohr's watchful mentorship. Experimentalists Dirk Coster and George de Hevesy discovered hafnium, providing the tangible proof required to validate Bohr's structural theories. Simultaneously, figures like Hans Kramers and Oskar Klein forged the rigorous mathematical framework of this new physics. This collective brilliance at Copenhagen turned abstract theory into the foundational laws of the subatomic world. By 1927, science reached a breaking point, the paradox of light and matter. We discovered that fundamental entities like electrons behave in ways that seem impossible to our classical minds. Depending on how we measure them, an electron acts either as a discrete particle or a continuous wave. These behaviors are mutually exclusive, illustrated here by the different shadows cast by a single cylinder. While both shadows represent a fundamental truth, they can never be observed simultaneously. This reality forces us to confront a world where nature's identity depends entirely on the experimental lens through which we view it, a universe defined not by singular certainty, but by complementary perspectives. We now arrive at a transformative shift in thought, a new epistemology, complementarity. This core concept reveals that properties appearing mutually exclusive are not contradictory, they are complementary. To exhaust all possible information about a quantum object, both descriptions are strictly necessary. This perspective anchors the Copenhagen interpretation, which posits that reality is never independent of the measuring apparatus. It is the very act of observation that forces an object to manifest in one state or another. Much like the dual halves of a yin-yang, these opposing natures work in tandem to define the fundamental essence of the physical world. We now witness the titanomachy, a clash of intellectual giants, Albert Einstein versus Niels Bohr. Einstein, a champion of local realism and determinism, maintained that the universe holds definite properties independent of our observation, famously insisting that God does not play dice. In contrast, Bohr championed complementarity and probability, arguing that reality remains indeterminate until the act of measurement, sharply retorting, "Stop telling God what to do." While Einstein's 1935 EPR paradox challenged the completeness of quantum mechanics, it was Bohr's probabilistic vision that ultimately triumphed, becoming the enduring foundation of modern physics. This debate remains the most significant philosophical divide in the history of science. In 1930, a legendary confrontation reached its peak in the photon box triumph. Einstein attempted to lay a final trap for quantum theory, proposing a thought experiment to measure energy and time with perfect precision, a direct violation of the uncertainty principle. After a night of genuine panic, Bohr delivered a masterstroke of a reversal. Using Einstein's own general relativity, he demonstrated that as the box recoiled, the change in gravity would shift the clock's time. This subtle effect preserved the uncertainty Bohr had championed. By using his opponent's greatest discovery to defend the quantum realm, Bohr emerged victorious, and the fundamental laws of physics remained secure. Niels Bohr's vision extended far beyond physics, establishing a universal framework to decode the complexities of the natural world. He argued that truly understanding any intricate object requires embracing diverse points of view that defy a single, rigid description. In physics, we see this in the duality of the continuous wave versus the discrete particle. In biology, Bohr contrasted mechanistic molecular study with the finalistic, purposeful essence of living organisms. Finally, in psychology, he noted that no sharp separation can exist between the perceiving subject and the objective content being observed. Ultimately, Bohr's principle of complementarity serves as a bridge, uniting these disparate fields under one profound philosophical umbrella. Between 1936 and 1939, Niels Bohr revolutionized nuclear physics by reimagining the atomic nucleus not as a rigid structure, but as a dynamic, incompressible fluid drop. This liquid drop model became the key to unlocking the mysteries of fission. In 1939, collaborating with John Wheeler, Bohr uncovered a vital distinction. While abundant uranium-238 remains stable, only the rare isotope uranium-235 splits when bombarded by slow neutrons. This specific insight was the missing link that made a self-sustaining chain reaction, and the entire atomic age, theoretically possible. By understanding how this tiny liquid drop could be torn apart, Bohr provided the blueprint for a power that would fundamentally reshape the modern world. In September 1943, Niels Bohr began a perilous flight from darkness. Facing imminent arrest in Copenhagen due to his Jewish heritage, he fled by fishing boat at night to Sweden, carrying a critical bottle of heavy water. His escape continued with a death-defying flight to London, cramped inside the unpressurized bomb bay of a Mosquito aircraft, where he narrowly survived oxygen starvation. Bohr finally reached the United States, arriving at Los Alamos to join the Manhattan Project. This daring journey preserved one of the world's greatest scientific minds for the Allied effort, transitioning from the shadows of occupied Europe to the secret heart of the atomic age. Operating under the top-secret pseudonym Nicholas Baker, Niels Bohr arrived at Los Alamos as the scientific father figure. He served as a crucial mentor to young physicists like Richard Feynman and, in February 1945, provided the technical clarity required to solve the stubborn modulated neutron initiator puzzle. Yet, for Bohr, the project was overshadowed by an ethical horror. He immediately foresaw the dangers of a post-war arms race, famously noting that the scientists didn't truly need his help to build the bomb. Consequently, he shifted his focus entirely to the political aftermath, advocating for global transparency to prevent the catastrophe he feared would follow the dawn of the atomic age. By 1950, we witness Niels Bohr's evolution from nuclear pioneer to global visionary in the fight for an open world. As early as 1944, Bohr lobbied Roosevelt and Churchill to share atomic secrets with the Soviet Union, hoping to prevent a post-war arms race, but his plea was soundly rejected. Undeterred, he published an open letter to the United Nations in June 1950, asserting that no international control could be effective without free access to full scientific information. Bohr warned that the alternative, perpetual secrecy, would lead humanity toward the grim reality of mutually assured destruction. It was his final, desperate call for transparency in a world irrevocably changed by the power he helped unleash. We conclude with the architect of the modern era. Niels Bohr was the ultimate personification of his own principle of complementarity, embodying the profound contradictions of a turbulent century. He moved seamlessly between the roles of visionary theorist and pragmatic institution builder. While his scientific genius helped unlock the power of the atomic bomb, he emerged as a relentless, lifelong champion for global peace. Bohr's legacy is absolute. Without him, we would lack the structural architecture of the atom, and without his philosophy, we would lack the essential language required to understand reality itself. He remains the man who gave the modern era both its blueprint and its boundaries.